Hello and welcome to the next talk in pattern recognition. This would be a last topic. We will look at parametric estimation, then we will move on to non-parametric estimation. So, to briefly recall what we have been doing in the last few classes, we have been considering estimation of density functions given IID samples from the density. We studied maximum likelihood estimation, Bayesian estimation of density functions. For all the standard density functions, we have seen how to compute the ML estimates as well as the Bayesian estimates. The idea is that given the estimated densities, we can implement the Bayes classifier with the estimated densities. Okay. While considering ML estimation and so on, we had also looked at the issue of exponential family of densities. As you have seen, that is a very good generic density model. All the standard densities are captured there. We looked at exponential family of densities, and we also studied the role of sufficient statistics in estimation in the last class. So, as I said, we are going to look at the last topic, namely mixture densities in the parametric estimation. So, today we will consider estimation of mixture of densities. The basic idea is that in many cases, the standard density models such as exponential or normal or gamma, whatever, do not necessarily capture the underlying data distribution. One reason could be, for example, most densities are unimodal and data distribution may not be unimodal. In such cases, it is often very helpful to consider a mixture of densities as a class conditional density model. So, that is, instead of thinking of a class conditional density as single normal, we may think of it as a mixture of normals or mixture of exponentials and so on. Okay. So, that is where mixture densities come, and in this class we are going to look at how one estimates mixture densities. Our main reason for looking at mixture densities is that through this problem we will introduce a very important algorithm in estimation, which is called the EM algorithm. EM stands for expectation and maximization. We will see the algorithm later. But this EM algorithm is a very important algorithm in estimation, useful in many probabilistic models, including things like HMM models, hidden Markov models, and graphical models and so on. While many of those things we may not consider in this class, since this algorithm is important, we will look at it from the point of view of estimating mixture of densities. So, this is the mixture density model. Consider a density model where the density f x is given by summation over k going from 1 to capital K, lambda k f k x, where lambda k are greater than or equal to 0 and lambda k sum to 1, and each of the f k's is a density. Of course, maybe same kind of density, different kind of densities, that does not matter, but each of f k's is a density. Since each f k is a density and all the lambda k's are positive, the summation lambda k f k will be positive. Also, if you integrate this out over x, each f k will integrate to 1, and since summation lambda k is equal to 1, f x will itself integrate to 1. So, essentially, because f is a convex combination of densities, it will itself be a density. So, this is a well formed density model. If lambdas satisfy these conditions for convex combination and f k's odd densities. Okay. We often call lambdas as the mixing coefficients and f as the component densities. Okay. Mixture densities are very useful, especially when data distribution is multimodal. That is, being having only one maximum, it may have many maxima. For example, if you consider most standard densities are unimodal, for example, normal, that is the normal density curve, which has exactly one maximum. Right. Everything falls off monotonically on either side of the maximum. Exponential density is a similar thing. Okay. Most standard densities, Poisson, binomial, all of them are unimodal. Okay. But mixture densities allow us to capture densities that are multimodal. So, here is a mixture of two normal densities. The blue is one normal density, the red is another normal density, and the black one, that's going like that, is a mixture of the two. Here I just taken 0.3 and 0.7 as the mixing coefficients. Essentially, if I taken the two means of the normal, sufficiently far off, on one side the sum is completely dominated by one density, on the other side the sum is completely dominated by other density. In between I get a smooth transition from one maximum to another. So, many data distributions which have such multimodal characteristic, right, can be easily captured using mixture of normal. So, this is a multimodal density, the mixture is a multimodal density, and when data density is multimodal, we can often approximate it with sum of normals like this. So, as a matter of fact, what I call Gaussian mixtures, mixture density model is a very often used density model for class exponential densities in pattern recognition problems. Okay. So, let us say we have a mixture of k normal densities, f x given theta is k is equal to 1 to k lambda k f k x, where each f k is normal with mean vector mu k and covariance matrix sigma k. Okay. So, the parameter vector theta consists of all the lambda k's which are called mixing coefficients, and the parameters of all the constituent densities, namely all mu k's and all sigma k's. The f k's are sometimes called component densities or constituent densities, and as I said lambda k are called the mixing coefficients. Okay. Now, let us say we have this density model, and let us say we have a sample of n IID data from this density model. Okay. That is the standard scenario in any maximum likelihood estimation. We have a density model and we have data, and then we form the likelihood and maximize the likelihood to estimate the parameters. So, the likelihood would be what? L theta given d is simply product of this density model, right. So, if I do product of this density model, this is what I get, product I is equal to 1 to n of the density model which k is equal to 1 to k lambda k f k x. Okay. As we seen, we often take log likelihood, in all our earlier examples taking log simplified the problem. So, let us take the log likelihood. If I take log likelihood, this product of course will certainly become sum when I take a log. So, I get sum of ln of this. Now, this kind of tells you why mixture density model estimation is difficult. See, what we have here is the sum inside the log function. Earlier we got sum log of directly the f k, okay, and f k being from the exponential family, for example, Gaussian, because f itself will be exponential something. If I take log, I get a very nice expression, and that is how we have solved analytically for the ML estimation of all the standard densities. But here, because there is a sum inside the log and we can't simplify it, the fact that f k is from an exponential family does not give us any analytical simplification. Okay. So, this means that maximizing log likelihood can become a difficult optimization problem. Earlier, because I directly got ln, suppose capital K is 1, then I would simply get ln lambda times ln f, and if f is exponential, that what is inside the exponent comes out, and as we have seen through sufficient statistics, that immediately gives rise to very simplified ML analytical expressions for ML estimates. But here we have a sum inside a log, and hence those simplifications do not occur. Then we may have to solve it numerically, and it can become a difficult optimization problem. What we will see in this class is we will take a specific example of this and try to solve it by explicitly calculating the partial derivatives, and out of that we will try and formulate a general procedure for all such densities. Okay. So, for our simplification we will consider one dimensional problem with only two component densities. We want both component densities to be normal. So, let us put a special symbol for it. Let us say phi of x given theta j is normal with parameters mu j and sigma j. So, theta j consists of mu j sigma j. So, phi of x given theta j is normal with mean mu j and variance sigma j square. This is the phi x given theta j, and let us say our density model is mixture of two such normals. So, f x given theta is lambda 1 times phi x given theta 1 plus lambda 2 times phi x given theta 2. So, this is phi x given theta 1 is normal with parameters theta 1, namely mu 1 and sigma 1. Phi x given theta 2 is normal with parameter theta 2, namely mu 2 and sigma 2. So, f itself will have parameters given by theta as theta 1 parameters of this density, the theta 2 parameters of this density, and the two mixing coefficients. That will be my parameter vector. Okay. Now, what is the log likelihood? As we just now seen is summation I is equal to 1 to n ln of lambda 1 phi x I given theta 1 plus lambda 2 phi x I given theta 2. Okay. So, this is what I have to differentiate with respect to various components of theta. What are the components of theta? Mu 1, mu 2, sigma 1, sigma 2, lambda 1, lambda 2. So, I have to differentiate this with respect to the components to maximize. Okay. So, to obtain the ML estimate of theta given this log likelihood, we have to maximize this with respect to theta. To maximize this with respect to theta, we have to calculate partial derivatives of L and equate it to 0 and see if we can solve for it. So, if I want partial derivatives, let us say with respect to mu or sigma of this, essentially this ln will give me 1 by that lambda 1 phi given theta 1 plus lambda 2 phi given theta 2 into derivative of phi given phi x I given theta 1 with respect to mu 1 or sigma 1 whatever. Similarly, derivative of phi x I given theta 2 with respect to mu 1 sigma. So, first let us calculate this partial derivative of these derivatives of phi with respect to mu 1 sigma. The way we put this theta 1 and theta 2, let us first notice that partial derivative of phi x given theta j with respect to mu s or phi x given theta j with respect to sigma s is 0 if j is not equal to s. So, if I want phi x given the derivative of phi x given theta 1 with respect to mu 2, because phi x given theta 1 depends only on mu 1 and sigma 1, its derivative with respect to mu 2 would be 0. Similarly, the derivative with respect to sigma 2 will also be 0, right. So, only phi x given theta 1 will have non-zero derivative with respect to mu 1 and sigma 1 only, and phi x given theta 2 will have non-zero derivatives with respect to mu 2 and sigma 2 only. So, we do not have to calculate the cross derivatives, we have to only calculate derivatives of phi x given theta j with respect to mu j and sigma j. That is easily done, simple differentiation of this. If I want derivative of this, let us say with respect to mu j, I get this factor as it is into exponential of this as it is multiplied by the 2 will come out, will cancel with this 2, x minus mu j by sigma j square, and another minus will cancel this minus. So, essentially what I get is the same phi x given theta j multiplied by x minus mu j by sigma j square, right. So, that is what I will get, del phi x given theta j by del mu j is phi of x given theta j into x minus mu j by sigma j square. Similarly, differentiating the normal function with respect to sigma j, we get minus 1 by sigma j square into exponential of this in one term, and 1 by sigma j root 2 pi exponential of this into x minus mu j whole square into minus 2 by sigma j cube in this term. So, in both of them the phi x given theta j will be a common factor. So, with that algebra one can show that phi x given theta j del phi x given theta j by del sigma j will once again be phi x given theta j multiplied by this x minus mu j whole square by sigma j cube minus 1 by sigma j. Okay. Given this, now we know how to calculate derivative with respect to this. If I want derivative of this with respect to mu 1, that will be, because this ln, the derivative will go inside the sum, ln will give me 1 by lambda 1 phi x I given theta 1 plus lambda 2 phi x I given theta 2 into derivative of this with respect to mu 1, derivative of the second term with respect to mu 1 will be 0, and derivative of the first term with respect to mu 1 we already know. So, doing all that, we get derivative of L with respect to mu j will be lambda j phi x I given theta j, that comes from here, into x I minus mu j by sigma j square. This is the del phi x theta j by del mu j. This comes because of the log. Okay. So, this is the partial derivative with respect to mu j. Similarly, we will get with respect to sigma j. If you want with respect to sigma j, once again this 1 by the lambda 1 plus lambda 2 term will be there, and with respect to sigma j, I once again get that lambda j phi x given theta j term, and instead of this x minus mu j by sigma j square, I will get this term, right. So, in all these terms, as you can see, we have this factor lambda phi x given theta j by lambda j phi x given theta j by lambda 1 phi x I given theta 1 plus lambda 2 phi x I given theta 2. Let us give a name to that term. Let us call it gamma I j. Gamma I j is lambda j phi x I given theta j by the sum of the two densities. Then the earlier equation can be written as del L by del mu j is summation I is equal to 1 to n gamma I j into x I minus mu j by sigma j square, right. Just by taking that factor out, we got a very simple equation. As I said, derivative with respect to sigma j will also be same. So, let us write that also. So, once again it will be summation over I gamma I j, instead of this term the derivative, the sigma j derivative term will come there. So, if I want to solve for this, I have to just equate them to 0. So, for example, if I equate them to 0, what do I get? Summation gamma I j x I minus mu j equal to 0 by multiplying with sigma j square, right. That will give me summation gamma I j x I is equal to mu j times summation gamma I j. So, I can easily solve for mu j, that is what I get. So, I know the ML estimate satisfy mu j is summation I is equal to 1 to n gamma I j x I by summation gamma I j. Similarly, if I equate this to 0, take sigma j cube this side, it becomes sigma j square. So, I get sigma j square times summation gamma I j is equal to gamma I j times x I minus mu j whole square. So, sigma j square will be summation gamma I j x I minus mu j whole square by summation gamma I j, right. That is that term. Okay. First, let us understand that we have not solved the problem at all. The gamma I j, right, depend on theta j. That means, they need to calculate gamma I j, need to know mu j sigma j for j is equal to 1 to 2. So, even though this looks like an estimate, it is not an estimate because the RHS depends on the parameters we want to estimate. But if I put the same mu j hat sigma j hat in the RHS, this is some equations that the mu j hat sigma j hat have to satisfy. That is why I wrote here ML estimates satisfy these equations, then say these are the ML estimates given by this equation, right, because both sides I will have the mu's and sigmas. But on the other hand, there is a very interesting structure here, right. See, for example, if gamma I j is equal to 1 for all I, it will be simply summation x I by n, which is the old sample mean estimate. So, there is a lot of structure here. So, let us look at the structure a little more closely. These are my estimates. Okay. So, first thing is they are like sample mean estimates. If I look at the mu j estimate, it is summation something into x I by summation the same thing, right. The sample mean would have taken this gamma I j to be 1, instead of getting 1, I am getting some other numbers. So, I can think same thing about sigma j square estimate. So, I can think of this as is a sample mean where all samples are not weighted equally. The sample mean, but the sample x I is weighted with gamma I j, right. So, if I think of giving separate weight to each sample, so when I am estimating mu j, I give the weight gamma I j to sample x I. Okay. So, we can think of gamma I j as how much responsibility x I has for estimation of the jth component density. So, if I think of gamma I j as weights, then this is essentially a weighted sample mean. See, somehow if gamma I j's are 1 and 0, so that I know these x i's are from the mu j density, then this would have been exactly the sample mean, but instead of that it has become a weighted sample mean with weights gamma I j, and the gamma I j is sometimes called the responsibility coefficients. Okay. Of course, if there is only one component, then j will being 1 to 2, j is 1, then gamma I j is all 1, then these are the same sample mean estimates we got earlier for ML estimation of mean and variance of a single normal density. So, they kind of in the limiting case of only one component in the density, they go back to the single density estimates. They still retain the nice sample mean structure with gamma I j being the weights associated with the ith sample, and if I think of these as weights, then these are essentially weighted sample mean estimates. Of course, they are not really estimates, as I said, because the gamma I j depend on mu I mu j. So, let us come back to this, but Let us remember that mu j and sigma j are not the only parameters. Lambda 1, lambda 2, the mixing coefficients are also to be estimated. So, let us complete our estimation. So, we have to maximize the log likelihood with respect to the lambda j's also. But maximization with respect to lambda j's is not straightforward, because lambda j's have a constraint. Lambda 1 plus lambda 2 is equal to 1. Of course, they also have a constraint that lambda 1, lambda 2 greater than 0, but we have to certainly satisfy the constraint lambda 1 plus lambda 2 is equal to 1, and hence is a constraint optimization problem. No problem, we already seen this when we estimated Bernoulli multinomial density. We had similar constraint and we used constraint optimization for it. So, what do? We form the Lagrangian. So, which means instead of equating to 0 the partial derivatives of the log likelihood, we take the log likelihood plus a Lagrange multiplier times the constraint lambda 1 plus lambda 2 minus 1, take the derivative of this and equate that to 0. So, if we do that, let us say we take derivative of this with respect to lambda 1. So, the second term only gives me eta, the first term is I want to differentiate with respect to lambda 1, that is fairly straightforward. We will get this. Let us look at L. If I differentiate with respect to lambda 1, I get 1 by this into d by d lambda 1 of this will give me phi x I given theta 1, right. So, this is phi x I given theta j by lambda 1 phi x I given theta 1 plus lambda 2 phi x I given theta 2 plus theta equal to 0. Since we already defined the gammas, this term is nothing but gamma I 1, because this is phi x I given theta 1. So, if there is a lambda 1 here, this term would have been gamma, because there is no lambda 1, we will write it as gamma I 1 by lambda 1 plus theta equal to 0. Okay. That means, summation gamma I 1 is equal to minus eta lambda 1. If we get a similar equation for lambda 2, meaning summation gamma I 2 will be equal to minus eta lambda 2. Now, using lambda 1 plus lambda 2 is equal to 1, we get eta is equal to eta times lambda 1 plus lambda 2. Now, eta lambda 1 is summation gamma I 1, eta lambda 2 is summation gamma I 2. So, that is what we get, and by definition gamma I 1 plus gamma I 2 is equal to 1. So, this gives me n. Okay. So, if I substitute that in this equation, I get my lambda 1 estimate. My lambda 1 estimate is 1 by n summation gamma I j, but both for lambda 1 lambda 2 I written one equation for lambda j. Right. So, we now obtained estimates for mu's, mu j, sigma j's and lambda j's. So, we can put all of them together into like this. Mu j hat is summation gamma I j x I by summation gamma I j, sigma j square hat is summation gamma I j x I minus mu j whole square by summation gamma I j, and lambda j is 1 by n summation gamma I j. As I said, of course, these are not estimates, because both sides involve the unknown mu's and sigmas, but we know that the final estimates for mu, sigma and lambdas have to satisfy this set of simultaneous nonlinear equations. Okay. This first note that, as I said, the structure is very interesting. See, lambda j, you are asking what is the chance that a given x I, a random x I comes from the jth component density. For each I, if x I's responsibility to j is gamma I j, then gamma I summation gamma I j by n should be the chance of a random x I coming from the jth component density, right. Similarly, we have already seen that these are simple sample mean estimators. So, somehow this gamma I j, the responsibility coefficients seem to give us some weight of how much of x I should I assign while estimating things for jth component density. Okay. So, the structure is interesting, even though they are not expressions for estimates, because both sides involve, but then we know that the estimates mu j, sigma j, lambda j satisfy the simultaneous equations. Given any set of simultaneous nonlinear equations, we can solve them iteratively using, let us say, Gauss-Seidel iteration. What does Gauss-Seidel iteration do? At each iteration, I use the values of the previous iteration, put them in the RHS of the equations, and then the LHS will give me my new equations. So, if I did that, I get these iterates. So, if I want the new mu j, that is the value of the k plus first iteration for my estimate for mu j, that will be gamma I j k x I by summation gamma I j k, where I am using the previous iteration values of gamma I j. Right. Similarly, for lambda j, similarly for sigma square j, and gamma I j k plus 1 is always given the current values of theta j's and lambda j's. I can calculate gamma I j k plus 1. So, this is an iterative procedure. I start with some initial guesses, then given the initial theta 1 0, theta 2 0 and lambda 1 0 and lambda 2 0, I can calculate gamma I j 1. Once I know gamma I j 1, I can calculate mu j 1 sigma j 1 lambda j 1. Using that, I will calculate gamma I j 2 and so on. So, this is a nice iterative method, which is essentially the Gauss serial iteration for solving the previous set of simultaneous equations. Right? We know that the ML estimate satisfy these simultaneous equations. These are only equations, because as I said, the gamma I j's on the right hand side themselves involves mu j, sigma j's and lambda j's. So, this is the set of simultaneous equations satisfied by mu j, sigma j, lambda j. So, we are iteratively solving it. Each iteration we use the previous values in the RHS, and that value we assign as the new value for the corresponding variable in the LHS, on the LHS. Okay. That is the standard Gauss serial iteration. So, if I did that, I get these iterative equations. Okay. Of course, these simultaneous equations have to be well behaved for the Gauss serial iteration to properly converge. What rate it converges depends on the nature of these equations and so on. These are of course nonlinear equations, they are not linear equations. But generally for most well behaved nonlinear equations, the Gauss serial iteration converges. So, we can say that this iterative procedure is the optimization procedure to optimize log likelihood and hence find the ML estimates of a mixture density, which in this is a specific example of mixture of two Gaussians. By the way, my component index is j, we have taken care to always write sum over j is equal to 1 to 2 like here. So, that whatever we have done easily extends to a k component mixture too. Okay. Of course, because all our these derivatives have come from Gaussian, these specific set of equations are particular to Gaussian mixtures, but even there they are not specific to only two components, is easily generalized to k components. We use it 2 only so that my equations do not overflow out of the slide. Otherwise, even if we have k component mixtures, we can still do this. Okay. So, this we obtain by simply differentiating the log likelihood function and equating to 0, and since we can't analytically solve it, we used a Gauss serial iteration to solve the resulting simultaneous equation that the estimates have to satisfy. Okay. That is what gave us this iterative procedure. Now, of course, there must be something nice about it, because as I said, these are essentially sample mean estimates, right. So, there is some structure here, something interesting happening here. So, let us try to take a look at that. So, as it turns out, what we have done is a special case of a very general procedure that allows you to do the ML estimation of any k component mixture, not necessarily Gaussian. Okay. In many cases of ML estimation of mixture of densities, it gives rise to the same kind of iterative optimization procedures, and we will now look at this general procedure. As I said in the beginning, this general procedure is what will lead us to the so called EM algorithm, expectation maximization algorithm. Okay. So, let us go back. Our original density model is f x given theta, j is equal to 1 to 2, lambda j phi x given theta j. I still put j is equal to 1 to 2. So, I am sticking to my example of two components, but as I said, is only because it is easier to write the expressions. As you will see, wherever I put the summation up to 2, if you put summation up to k, it is easily generalizes to k component mixtures. Okay. So, when we have our samples, each xi is drawn IID according to this density. Okay. So, I can ask how would I draw such samples? If this is my density model, how would I draw samples from it? Because there are different densities from which to draw. We are assuming that if phi's are normals, we can always generate random numbers with respect to a particular normal density. So, given any density, there are ways to generate random numbers. How do I generate with respect to mixture density? One way of thinking about it is, what I will do is, to generate each xi, I will first choose a component density. I have to decide whether the next xi, say x1, x2, whatever the next x, comes from phi x given theta 1 or phi x given theta 2. This decision I have to make with probability lambda 1 or lambda 2. That is, with probability lambda 1, I choose the first density, probability lambda 2, I choose the second density. That is why lambdas are positive and sum to 1. So, using lambda 1, lambda 2, so on, as the probabilities for choice, I choose a component density and then I generate it from the component density. So, each xi, finally what I get is generated either from one of these phi x given theta 1 or phi x given theta 2. Only thing is, I do not know which xi is generated from which density, right? Because that I am not told. Probabilistically, some xi are generated from phi x given theta 1, some xi are generated from phi x given theta 2, and this is this probabilistic or stochastic choice is controlled by lambda 1 and lambda 2. That is how I am going to generate my sample. That is how IID samples come from such a mixture density estimation. However, I am only given x1, x2, xn. So, I do not know whether x1 is come from the first component density or second component density. But just for a moment, pretend that somebody tells us this. If somebody tells us this, then the estimation is absolutely trivial. Then, given my full data, I can separate it out into data of xi that have come from phi x given theta 1. Now, that is simply estimating a single normal density. So, I know how to do it. So, if I can separate data as data that come from the first component density phi x given theta 1 and data that come from the second component density phi x given theta 2, then estimation of the parameters is very simple. Now, this is a very interesting characteristic. So, we have a situation here where essentially I have a mixture density, and to actually estimate it, I have to go through a complicated iterative, otherwise I have to go through an iterative procedure. Whereas, if somebody tells me which xi have come from which component density, the estimation is trivial. Okay. So, let us try to formalize this. Let us say we define random variables Zij, I going from 1 to n and j going from 1 to 2. Recall that n is the number of data samples we have. So, we define random variable Zij. The idea is Zij gives me information about which component density I has come from. So, if I look at Zi1 and Zi2, I can tell whether xi has come from first density or second density. How am I doing this? For each I will make Zij1 if xi came from jth component. That is, if xi came from the first component, then I will make Zi1 equal to 1 and Zi2 is equal to 0. And if xi came from the second component density, then I will make Zi1 equal to 0 and Zi2 is equal to 1, right. So, each Zij is binary like that, and we have summation j Zij is equal to 1. Of course, it looks needlessly complicated. I have only two numbers Zi1 and Zi2, and from the way I have defined it, because each xi, if xi has come from the first component, is not coming from the second component. So, I might as well use only one number Zi. The reason why I have used two numbers is that this naturally generalizes to k components. If I had k components, that I would have Zi1, Zi2, Zik, only one of them is 1. So, this is a representation of a binary vector, much like what we saw in the multinomial density estimation. So, even though there are only two components and I know Zi1 plus Zi2 is equal to 1, let us still stick with the notation of Zij for our indicators. So, Zij is 1 if xi came from the jth component for j is equal to 1 to 2 and Zi1 plus Zi2 is equal to 1. Okay. Now, by definition, what is the probability Zij is equal to 1? Zij is equal to 1, the event Zij is equal to 1 is that the xi comes from the first from the jth component. component density. Now, because each xi are IID, irrespective of what the remaining samples are doing, for that xi with probability lambda j, I choose the jth component density. So, probability z I j is equal to 1 is lambda, that is probability z I 1 is equal to 1 is lambda 1, probability z I 2 is equal to 1 is lambda 2. And the second thing that is interesting here is the density of xi, unconditional density of xi, I know what it is, that is my density model. But if you give me z I j's, conditioned on z I j is equal to 1, what is the density of xi? Z I is equal to 1 means xi is coming from the jth component density. So, conditioned on z I j is equal to 1, the density of xi is simply phi xi given theta j. So, condition on z I 1 is equal to 1, density of xi is phi xi given theta 1, and condition on z I 2 is equal to 1, density of xi is phi xi given theta j. That is how these z I j's can also be equivalently specified. Okay. We can think of z I j's as the missing information. Essentially, the density estimation problem for the mixture densities has become difficult because I am not given the z I j information. I am only given xi's. If I am also given the random variable z I j for I is equal to 1 to n and j is equal to 1 to 2 here, or in general 1 to k, then as we can see the estimation is easy. So, we can think of z I j as the missing information. Let z I denote the vector of component z I j, in our case z I will be z I 1 z I 2, okay. And let us say d superscript c denote the data written as x 1 z 1 x n z n. The c means complete. So, I am thinking of x 1 x n is the data I am given, but there are some missing components there. If you put in the missing components, then my new data is become d superscript c, c for complete. We will see complete again later. Our data consists of only xi, but suppose for a minute that the sample data that we are given is actually x 1 z 1 x n z n, then obviously estimation is trivial. What will be mu 1 hat? Summation is equal to 1 to n z I 1 x I by summation is equal to 1 to 1 z I 1. Only if z I 1 is 1, the xi has come from the first component. So, I pick all my sample that I come from the first component and take their sample mean, that is the mean of the first component, that is the ML estimate for the mean of the first component. Similarly, mean of the second component. Right? This is very straightforward by the definition of z I's. So, if z I's are given, the estimation is trivial, but more importantly, as you can see, these equations are exactly like the equations we saw earlier, except that wherever I am getting z I j, there I am getting gamma I j. Because I did not have z I j, I am kind of using the ratio of likelihoods as so to say the probability that ith one comes from component 1 or component 2. That is what gamma I j's are giving me. Okay. So, these equations tell me that if the missing information z I is given to me, then I can trivially finish my estimation of all the component densities. Of course, I have written only for mu's, but similarly I can write for everything sigmas as well as lambdas if z I's are known. Okay. So, now let us put all this intuition together into characterize the general situation that we have. The data that we have is somewhat what we call incomplete, right. That does not have all the information that we would ideally like to have to make our job of estimation easy. Okay. So, the data we have is incomplete. It is incomplete because there are some hidden or missing data or hidden or missing variables. Right. If we are given the complete data, what we call DC in the previous slide, namely the original incomplete data plus the missing data, then ML estimation is very easy. This is the general situation. Okay. In our example, xi's all the xi's together constitute the incomplete data, and if I have given xi z I, that constitutes the complete data. So, z I are the missing or hidden data or hidden variables. Okay. So, that is the general situation. So, we are given incomplete data, we can hypothesize some missing data like the z I j variables here, such that if I have given xi z I as my actual complete data, then the estimation is simple. Okay. This kind of thing is true for all mixture density estimation, right. So, now we are seeking a general method whereby if I can hypothesize some variables z I at the missing variables in such a way that if I am given x I z I together, my estimation is very simple, but I am only given x I, what can I do about estimation? That is the question we like to ask. And the algorithm that specifically addresses this question is called the EM algorithm. It is an efficient iterative procedure for my maximum likelihood estimation in such situations. The algorithm basically has two steps, so called expectation step and maximization step, and that is the reason for the name EM, expectation maximization is called expectation maximization algorithm or EM algorithm. Okay. The notation is that xi is equal to 1 to n is the incomplete data, xi zi is equal to 1 to n is the complete data. Okay. So, the EM algorithm is like this. So, we have a notion of incomplete data, which is the actual observed data, and we have notion of complete data. By hypothesizing some variable, some extra random variables z I, we define what is called complete data. Okay. So, an EM algorithm starts with deciding what is my complete data. So, obviously, the incomplete data is whatever data I am given. My complete data consists of incomplete data plus the missing variables. So, I design the missing variables to in such a way that if the complete data is given, then my estimation becomes simple. So, let f x z given theta be the density for the complete data. What do I mean? That the complete data, that x I z I is equal to 1 to n, or n IID samples from this density. So, the way we hypothesize z, we should, because we already know the density for f x given theta and we are hypothesizing z. So, we should be able to calculate the density model for the complete data. Once we get the density model complete data, this is the density model for the log likelihood for the complete data. Product I is equal to 1 to n f x I z I given theta is the likelihood for the complete data, and putting a log, I get a log likelihood for the complete data. Okay. Recall that earlier we have been we said that the data x 1 to x n can also be represented by a bold x. Similarly, the data d c, which consists of x 1, z 1, x 2, z 2, x n, z n, the complete data will represented by bold x comma z. Okay. So, in that sense, the complete data log likelihood can also be written as log of this product will now become f of bold x bold z given theta. So, we will use this notation also wherever near, mostly we will use this notation for the complete data log likelihood, okay, and similarly all the other log likelihoods. Okay. So, the EM algorithm setup is we have incomplete data x, xi, x1, x2, xn, and we have the model f x given theta, that is the density model. We hypothesize some missing variables z, then we compute the complete data density model f x given z, f x z given theta. So, now we have the complete data model, that the joint density of x and z, because z is what we hypothesize, f x given theta is the given density model. So, we have now the density for x, the joint density for x and z, and of course, all the other conditional densities we can compute from there. For example, we can compute, given this, we can compute the conditional density of z x given theta, where we are essentially hypothesizing the missing variable z. So, EM algorithm says that if I have the notion of the complete data and the incomplete data, how do I actually estimate, given that I can only use the incomplete data, I do not know the values for z. Okay. So, this is how the EM algorithm works. The two steps of the EM algorithm, the E step and the M step, E for expectation, M for. So, it is an iterative algorithm. So, at a given step, I am in the kth iteration, let us say, my current values for the estimated parameters are represented by theta superscript k. This is the current estimated values. Given the current estimated values theta k, I compute a function of theta, which I call q theta theta k, because while the function of theta, it also depends on the current estimated values. So, I call the function q theta theta k. What is this function? It is the expectation of the complete data or log likelihood, that is, you take expectation of this quantity ln f x z given theta, right. It is the expectation of the complete data log likelihood with respect to the conditional distribution of hidden variables conditioned on the incomplete data and current value of theta is theta k. In symbols, what it means is q theta theta k is the expectation with respect to only z, but using the distribution of z conditioned on x and theta k of the complete data log likelihood. So, in this complete data log likelihood, all the terms involving z are averaged out by the expectation, and to average out I use the conditional distribution of z given x and theta k. So, only in averaging out the z terms here I use this conditional distribution. The rest of the terms depend on this theta. So, this conditional expectation will ultimately be a function of both theta k and theta, that is why it is called q theta theta k. So, to say it again, q theta theta k is the conditional expectation of the complete data log likelihood with respect to the conditional distribution of the missing variables or hidden variables conditioned on the incomplete data and this iteration values of the parameters. Once we got this, the m step computes the next value of theta, that is theta k plus 1 by maximizing this function over theta. So, theta k plus 1 is computed as maximizer of q theta theta k over theta. So, this is the argument or the max over theta of q theta theta k. So, I take this function as a function of theta, find which value of theta maximizes this function, and that is given at the next iteration theta k plus 1. These are the two steps, each step one m step. It is a little complicated because of this funny conditional expectation. We will look at the example once again. We will go back to our 2 component Gaussian mixture example and compute these 2 steps, okay, so that we understand how to compute these 2 steps. So, let us consider the example of estimating 2 component Gaussian densities. This is our given data model, this is how our incomplete data is generated. So, xi is the given data which is the incomplete data. The zij's that we have defined earlier are the hidden variables or the missing variables, and xi zi constitute the full data. Okay. Now, recall that zij is an indicator of which of these j component densities that xi comes from. Okay. So, let us remember by definition of zij we have probability zij equal to 1 is lambda j, that is xi coming from jth component as probability lambda j, and condition on zij is equal to 1, xi is the density is the jth component density. Okay. Given these 2, we can now write the marginal density of z as follows. Remember that my complete data is xi zi, zi has 2 components zi 1 zi 2. If I want to write marginal density, then f zi given theta is phi j is equal to 1 to 2 lambda j zi j. This is, if I take away the product, it will be lambda 1 zi 1 into lambda 2 zi 2. Only one of zi 1 and zi 2 is 1, the other is 0. So, if zi is 1 0, this becomes lambda 1, zi is equal to 0 1, this becomes lambda 2, that is exactly this. So, I can think of this just like in the Bernoulli model, I can take the marginal of z like this, and conditional of x conditioned on z and theta, once again xi condition on zi theta is product phi xi given theta j to the power zi j. Once again zi j's are 0 and 1, for each I only one j is 1. So, whichever one is 1, I get that particular component density. So, I have got conditional density of x given z's and I have the marginal of z's. So, by multiplying I get the joint, right. So, the joint density model is I have to multiply these 2, both are product. So, the lambda j also comes inside this. So, that is the density model for the complete data. So, this is how I compute the density model complete data, because given the density model for the incomplete data and because I am hypothesizing which are the missing variables, that is how I compute the density model for the complete data. Okay. So, the the complete data likelihood will be, this is the symbol we are using for the complete data likelihood, f bold x bold z is product over I is equal to 1 to n of f x I z I given theta, which is product over j is equal to 1 to 2 of this. So, this is my complete data likelihood. If I want complete data log likelihood, that is the complete data log likelihood. Okay. Now, before we will go to our E and M steps, let us look at this expression. Now, we have got rid of the sum of log. Instead of sum of log, we have got log of sum. See, now log directly applies to phi's. So, if because phi is exponential, I can now simplify this. The moment I hypothesize Zi, my complete data log likelihood is the old structure of sum of log rather than log of sum that I was getting if I used only the mixture density. So, this is actually how the knowledge of Zi has made the estimation simple, because the complete data log likelihood is the usual form of sum of log, and we have done enough examples of how to maximize such things. Okay. All right. So, now let us do the E step. In the E step, we have to take expectation of z with respect to the distribution conditioned on x at a given value of theta. So, what is expected value of Zij conditioned on x and some theta prime? Zij is a binary value random variable. So, its expectation will be probability it takes value 1. So, the same as probability Zi is equal to 1 conditioned on x and theta. Now, x's are x1, x2, xn, they are IID, and hence Zij only depends on xi, it does not depend on others. So, this is probability Zij is equal to 1 conditioned on xi and theta prime. Now, this expression now I can invert using Bayes theorem. So, using Bayes theorem I can write this as f of xi given Zi is equal to 1, probability Zi is equal to 1 and summation over j of the same thing. F of xi given Zi is equal to 1 and at a theta prime is nothing but phi xi given, because j is equal to 1 theta j prime, and this is lambda j, right. So, what does this gives me? Lambda j from this term, and this will give me phi xi given theta j prime, and the denominator is sum of the same thing over j. This expression is very familiar, right. This is exactly the gammas that we defined earlier. Okay. So, Zij condition on x and theta prime is gamma ij of theta prime. Now, I will write it as a function of theta prime, where gamma ij theta prime is lambda j phi xj given theta j prime by summation over j of the same thing, right. First, notice that this is the same gamma ij's that we defined earlier. Only thing is, earlier also I was saying gamma ij's are functions of the parameters. This time, this our notation makes it absolutely clear that they are functions of thetas, right. Now, we need to do this expectation on the complete data log likelihood, right. Is the complete data log likelihood this. So, to take expectation of this, expectation only of jets. So, only this term will get into the expectation. So, in the q step, what will I get? If I take expectation of log likelihood, that is q theta theta k is I is equal to 1 to n, expectation goes in, j is equal to 1 to 2, expectation goes in, expectation of Zij given x comma theta k, rest of it is not function of Zij. So, that comes out of the expectation. All right. This is the, as you can see, this is the conditional expectation of the log likelihood of the complete data conditioned on x and theta k. That is how, see, this term is dependent on theta k. What comes out of that expectation still depends on old theta j's, the variable theta j. That is why this is a function of q theta theta k. All right. So, now this we already calculated, I can substitute for it. If I substitute for it, I get this. So, my E step is complete. I have computed my q theta theta k. In the M step, we have to find theta k plus 1 that maximizes q theta theta k over theta. This is my q theta theta k. As you can see, this gamma ij's have now come in at the expectation of those Zij's conditioned on x and theta k. Okay. Now, if I substitute for my Gaussian, this will be ln lambda j minus for the Gaussian this will be ln sigma j root 2 pi xm minus mu j by sigma j square. So, this is a very straightforward maximization do. Note that gamma ij's are only a function of theta k, they are not function of theta. When I am doing maximization with respect to theta, these are constant, right. So, if I want to maximize this with respect to mu, only this term will contribute a derivative with respect to mu. So, if I did that, this is a very straightforward optimization problem, simply because these are no longer functions of theta. This is like doing a single Gaussian estimation, and we get that, right, because if I differentiate with respect to theta, right, say with respect to mu, this will be 2 will come, the 2 will cancel, xm minus mu j by sigma j square, and this gamma ij theta k as coefficient, right. So, that will give me mu 1 k plus 1 is this. It's exactly like the expression we got earlier, right. So, the earlier expressions we got are what the EM algorithm gives us, right. Similarly, if I had done with respect to sigma 1, I would have got the sigma 1 derivative, and once again I would have got the same expression as earlier, okay. So, now I can go back and rewrite those equations, right. Now, I will just wrote gamma ij k plus 1 as gamma ij theta k plus 1, right. This is the same slide that we had earlier, except the last line. This tells you that the earlier iterative algorithm we got is actually the EM algorithm for this particular example, okay. So, I will stop here for this lecture. We completed this example. So, next class we will just briefly review this again and ask in general what the EM algorithm is about, and then briefly see why the EM algorithm should converge and why it gives us a very nice way of doing mixture density estimation. Thank you.